Thanks, Barbara, for kind introduction, and thanks, Miha and the Candela Foundation for enabling this open lecture. So today I'm going to talk about our, the community and our recent work on a new room temperature playground for Bose-Einstein condensate using halide perovskite. I think talking about BEC, Bose-Einstein condensate, in 2025 is a special year. 100 years ago, Werner Heisenberg laid the foundation for the whole quantum mechanics. And then today we have like Hogoland 2025, a new meeting to celebrate 100 years of the birth of quantum mechanics. And at the same time, 100 years ago, Bose and Einstein, two genius people, also proposed the concept of Bose-Einstein condensate. So I think 100 years later, it's a good time to see the community where we are, and then to also share the new progress to all of the people around. And I think for the 2025, it's also a special time for me. So at that time, I graduated from UC Berkeley as a PhD student, and then at the same time, I read a phenomenal paper from Professor Vinod Menon and his students, Xiaoze Liu. And then later on, we joined the same lab as postdoc and start to do polariton with strong matter-matter interactions coupling in the two-dimensional atomic crystals. And those are all inspired by Xiaoze's paper. And before that, I was working on near-field optics. So I think it's also 10 years from the initiation, I step into the field. And then I think it's a good way to summarize the community and then also my own effort. So a little bit introduction on this. I think as we all know, fundamental particle can be all classified into fermion and bosons. For fermion, because Pauli exclusion principles, you cannot place two particles at the same quantum states without different parameters. So typical fermion are electron and helium-3. While for bosons, there's no such a restriction. You can put arbitrary number of bosons in a single quantum state. So because these features, you can, once the system energy is trying to be lowering and lowering, the particle start to occupy the minimum energy of the states in the boson system. So they start to show a massively occupied ground states. Take the ideal gas as an example to illustrate this massively occupied ground states. For example, at the very beginning, if you have a really high temperature, you start to follow just simply Bose-Einstein condensate with the population density and the energy distribution like that. And then if you start to lower the temperature, the low energy states start to be more populated, and then the high energy states start to be lessly populated. So genius people like Einstein and Bose propose if you lower the temperature continuously, at a certain time, one part of the ideal gas will condensate, massively occupy the ground states, and then the rest remain saturated ideal gas. Although the genius concept has been proposed back to as early as 1925, the experimental realization only happened 70 years later. It is first done by the cold atom community, by the Ruby atom. So essentially by laser cooling and magnetic evaporative cooling, and then you trap a bunch of the cold atom in the really low temperature, and then start to cooling it down about 200 nanokelvin. What you will show is at the kx, ky equal to 0 location, where is the system's energy minimums condition, you will see a massively occupied ground states. And then as the temperature continue lowering, you see this occupancy become more and more pronounced. And for this great discovery, 2 Nobel Prize was given, one for the laser cooling in the 1997, the other one for the BEC demonstration, direct demonstration. The unique thing about the BEC with the cold atom is originally, if you start a quantum mechanics, you have to go to very small particle, which follow the basic rule about quantum mechanics. But it's also very small particle like electron, nucleus, While if you have a BEC, what is the good thing is you have many particles, they start to macroscopically, coherently follow one quantum state's nature because they all occupy the same ground states. Now you have a sizable quantum object you can study, without going into very small object to study. So that's the big advantages of it. So soon people also realize if you have a cold atom BEC and you combine with later interference to form optical lattice, what's going on is you are going to form a two-dimensional lattices. So essentially to enable a lot of the concepts, so-called quantum simulator or quantum emulator. So essentially this weakly interacting particle distributed in among a two-dimensional array will start to be able to emulate a lot of the Hamiltonians. So, which is, the fundamental concept about many of the solid state system that is harder to be understood. So if you trust my copy paste capability, and if we revisit the critical transition temperature of about the whole Bose-Einstein condensate system, we will quickly realize for three-dimensional Bose-Einstein condensate gas, the transition temperature into Bose-Einstein condensate is critically only rely on two physical parameters. One is the effective mass of the particle, and then the other one is the density of the particle, and then the rest is constant like Planck constants, pi, and Boltzmann constants. So that indicates to us is if you have a boson system that has a lot of particle, and then your critical transition temperature will go higher. And if the effective mass will be lower in the boson system, you will have transition temperature going up as well. So that means we don't necessarily go to a ruby atom at 200 nanokelvin, 9 order magnitude lower than the room temperature. So if you have another boson system, that will be a much higher temperature, and then we could even conduct experiment even up to room temperature or higher. So smart people quickly think about if we have higher density, lighter particle, how about directly go to higher transition temperature. So one of the subfield gradually emerge, because this thought is to couple two boson systems together, so-called cavity exciton-polariton. So the basic idea is if we have a semiconductor that's possess the exciton, so essentially exciton is the electron hole pairs resides in the band edge. So when you excited them with laser and create a excitation in this semiconductor in them. So if you also have a cavity, you will also trap photon, right? And the cavity, typical cavity we use in the field is the Fabry-Pérot cavity. So essentially a two flat mirror. So if you embed this exciton into a semiconductor into the cavity, and then if you make the cavity very good, and then the semiconductor also, majority of the emission during the exciton recombination go into the photon. So what will happen is your exciton will emit photon, and the photon trap in the cavity and reabsorbed by the semiconductor and regenerate the exciton. And if the generation back and forth, the rate is much larger than the exciton non-radiative decay rate. That means the exciton non-radiative decay and generate photon without give photon. And plus the photon decay rate out of the cavity. So essentially once the photon escape from the cavity, you are going to see a photon loss. So if the coupling rate in between the exciton and the photon are much larger, then those two loss channel we are going to entering a new regime we call the strong coupling regime. Essentially, we are going to form a new quasiparticle called the polariton inside the cavity. That is means in another way to say it is any photon escaped from the cavity that will experience the energy states of both the previous exciton and the photon, and one can write it as a linear combination of a hybridized states. So essentially, it's photon states with a certain portion and the exciton state in another portion. So think about it. If we have a semiconductor, we try to measure the semiconductor's emission with a different angle. So essentially with different polarization, with different projection in the horizontal in the K space. So if we plot the K and the E diagram, so essentially the momentum versus the energy diagram, we are going to observe the exciton become a flat line. So that means, no matter what angle you measure the semiconductor's exciton emission, they essentially show the same peak. If we remove the semiconductor, just put a dielectric there, what's going to happen is we are going to measure a photonic band with a dispersion. The reason behind it is if you try to see the photon with a cavity over a different angle, what we are going to see is the effective angle, the effective cavity length is going to be different. For example, if you normalize see this cavity, you see an effective length here, and then if you come with the angle, you see the effective length of the cavity become here. So essentially, the parabolic line shape represents the effective length change in the cavity. But once you form a strong coupling regime, the originally EK diagram will be renormalized into a hybridized state. Essentially, we are going to form an upper polariton and a lower polariton. And what's going on is this polariton state, because they coming from the hybridization of two bosons. One is exciton, one is a photon. So they still maintain the boson state. And while the other case is because we have now the photon that have a dispersion, and then we know the photon has a very light effective mass, and then the polariton will also form a similar dispersion. And then if you write down the effective mass formula, you quickly realize the effective mass of the photon because the photon nature, and then the polariton will has also a very small effective mass, 9 order, 8 order magnitude lower than the cold atom case. So in this case, the exciton part provide interaction and nonlinearity where you can effectively pump the system and generate a lot of the particle density, while the photon part provides small effective mass. So in this way, the polariton will inherit both the good aspect from the exciton and the photon, where you can see a lot of this high temperature things with the Bose-Einstein condensate, which is actually what we are hoping for. So in other words, to understand the cavity exciton polariton, so here is the dispersion, and then we have the exciton and the photon detuning and the Rabi splitting. One can think it even in a classical way without going to the complicated things. We have now two linear oscillator. One is the exciton, the other one is a photon. Now we bond it with another, spring, and then they have a much strong, strength. And then now we form a hybridized state called exciton, upper polariton and the lower polariton in the strong coupling regime. And experimentally, to observe those strong coupling optically in the exciton-polariton community is also very easy. Suppose we have a microcavity sample. We try to see the emission angle from this cavity, and because the K space, because the same emission angle will form in the back focal plane a spot. So what's going on is with the same angle, you will easily project it into a K-space circle, and then in the spectrometer entrance, you just select this slit and disperse out. So we will have the K selected by the spectrometer entrance, and then the E selected by the spectrometer dispersion of it over the different wavelengths. So in this way, one can measure just simply by K-space imaging, back focal plane imaging, and with the spectrometer, you can gradually you can easily see the EK diagram in the exciton-polariton system optically without complicated measurement. With this as a background information, indeed, the first convincing exciton-polariton condensate happened to be done with catatelluride quantum well, where the researcher decided to maintain the system temperature at a constant temperature, but gradually pumping the semiconductor quantum well system to increase the particle density in the system. And the experiments clearly show as the particle density gradually increase, the massively occupied ground state start to be emerge out at the K equal to 0 location, where they corresponding to the energy minimum of the system. And more excitingly is because now the particle are interactive with the exciton's Coulombic nature. And then you will see a little bit blue shift because once you have the first exciton, you put the second exciton in because the interaction, you have to make the system's energy a little bit higher. So that means the system is interactive and then also can run into the Bose-Einstein condensate, which very much represent all the nature you have with ruby atom as well. So many other work also has been done, along the field, such as the science paper and then the Nature Material paper back to 2002, and in the organic even, up to room temperature 2014. The first polariton condensation has been done without showing the thermal equilibrium in the catalyte, quantum well. Later on, people in the community also show if you make the quantum well structure and with the growth of the DBR over a very long time, and so that means you get rid of the stress residing in each of the DBR layer in the faster growth. You try to tune the growth parameter and to make everything, really, really slow growth. And then the Q factor of the system can become really high. So which means you really trap the photon and in the cavity for a long time. And then the exciton-polariton hybridized system in this way has a really, really long lifetime. With such a system, you can even see they truly go to thermal equilibrium Bose-Einstein condensate with all the occupancy precisely follow the BEC dispersion curve. So the system do work with quantum well, in summary. And then the other interesting thing with the system is now we have the upper polariton and then the lower polariton state instead of traditionally exciton and the V-coupling cavity photon. So once you pump it, the system, you generate a lot of exciton reservoir, and then the exciton reservoir relax and form a bottleneck region, and then eventually run into the condensate. And the system rely on a stimulated scattering compared with the stimulated emission. So more precisely is your bottleneck region, you will have the particle gradually, gradually filling the ground state. At the same time, they scattering into the higher energy state. So such a different mechanism result in the you can demonstrate the population inversionless laser in the quantum well system and in many other systems. So essentially, the polariton lasers threshold, once you go into the massively occupied BEC states, you rely on the stimulated scattering or cooling mechanism, where it's related with the exciton sheet density about the Blois wavelengths in the quasiparticle. While in the photonic laser, you have stimulated emission, you related with the Bohr radius of the exciton density. So essentially, in the polariton laser, you will have a much lower threshold compared with the same structure with the photon laser, as demonstrated in the researcher. So with those exciting discoveries, people quickly, after the birth of this polariton condensation, although it's 19 Kelvin, but it's still, it's much higher temperature compared with 170 nanokelvin or around 200 nanokelvin for the cold atom, but it's still a much lower temperature compared with room temperature. So there's soon after this, there's a lot of people start to searching for room temperature exciton-polariton BEC. However, to demonstrate the room temperature exciton-polariton BEC, you need to have a system that has a stable exciton against the thermal fluctuation. For room temperature, the thermal fluctuation is about 26 MeV, milli-electron volts. And there's many inorganic systems that don't sustain this room temperature thermal fluctuation. That means if you don't have a stable exciton, you don't have exciton-polariton for you to emulate a lot of these cold atom experiments. And many of this above room temperature thermal fluctuations, exciton binding energy material, for example, gallium nitride and zinc oxide, suffer from the inhomogeneities in the material growth. As that means the DBR or the material themselves has a much poor quality compared with the traditional gallium arsenide or catatelluride. And many of the emerging material, for example, the one that I used to work with is the TMDC material, have exciton, really high binding energy, but they suffer from low quantum yield compared with gallium arsenide. So many materials have been tried to realize the ultimate dream for room temperature exciton-polariton BEC, but they all have certain limitations. So specifically, for example, take the gallium arsenide, for example, researcher has been demonstrated back to 2007 in the PRL paper, 1 year after the 2006 Nature paper of the cat-telluride quantum well, where they show the gallium nitride, the bulk crystal integrated with DBr can run into polariton lasing. But from their experiment, you can see the line width of this material is really broad, and the Q factor of this cavity is really poor. So that means the nitride growth still very hard for the DBr, and also the quantum well structure are not ready, and then the gallium nitride tend to be a little bit higher order of homogeneity and the disorders associated with that. So people compare with the gallium arsenide and the cat-telluride, think it's okay to demonstrate the polariton lasing at the room temperature, but to study a lot of the polariton physics or Bose-Einstein condensate physics, this material is not so ideal. Same thing with zinc oxide. Zinc oxide, if you grow them with a various method into two-dimensional field, and then you measure on top of the surface, they tend to show quite a bit of inhomogeneities. So people get rid of this two-dimensional difficulty by running into synthesis with one-dimensional nanowire and demonstrated the polariton lasing in this physical review letters paper. But this one-dimensional nanowire configuration also has a lot of the limitation in studying the polariton physics. For example, if you try to construct a potential landscape, one-dimensional system tend to be very hard. And the other room temperature efforts goes into organic polariton, and as early as the Nature Photonic paper demonstrated by the Stephen Forrest and Stephen Cohen back to 2010, essentially you can embed a lot of this organic material into the dielectric cavity structure, and demonstrated the polariton lasing even up to room temperature. However, as we all know, this organic material tend to have exciton that is very localized into certain molecule. That's a good and a bad. The good thing is the organic, if you have certain defect, the organic molecule are not sensitive. For example, if you have one molecule that is being burned by laser, and then you still have, the system still have 99 molecules. This 99 molecules still behave like a Franco exciton very well. You have quantum yield 99%, almost not demonstrated, almost not deteriorate by this burn of one molecule. But that's also bad because these are Franco excitons, which means the excitons don't interact with each other. The emission probably only rely on the one molecule instead of many molecules together in this cavity region. So they have limited interaction strength. So for a lot of the Bose-Einstein condensate, the physics experiment, you need the particle to have certain strengths of interparticle interactions. So those systems are relatively poor in terms of that. Plus, as I said, there are organic molecules. You need to pump it really, really, really hard, and then to see this condensate in a small region. And soon after this, you start to show degradation because the poor photostability of this organic molecule intrinsically. Another system that people hope a lot is to do this in the two-dimensional material. Essentially, is the transition metal ditroconide monolayer. So, however, because the system has a monolayer, and we all know monolayer, if you fabricate a sample with certain things on top, you tend to introduce defect on top of the semiconductor, which make the quantum yield degrade. And plus the two-dimensional material, if you have a big exciton binding energy, that means the exciton annihilation also become promoted because your exciton tend to interact and generate a phonon. So combine the two things as a drawback. So we typically, even they publish really good paper to show really strong Rabi splitting. The photoluminescence properties appear to be really broad in those 2D material, and especially compare with the gallium arsenide, the line width sometimes is not so ideal. So back to the 2017, Xiaozi and I at that time still work as a postdoc at UC Berkeley. We try to overcome this 2D materials fabrication issue by using e-beam resist. So essentially a spin cold polymer-like material. Once you so-called HSQ, once you thermally heat up, they converted into silicon dioxide material. So by spin coat HSQ and transfer 2D material on top, and then spin coat another HSQ, we minimize the thermal evaporation or e-beam evaporation's bombardment on the two-dimensional material, and in this way minimize the sample degradation during the fabrication. And to further protect the material from sample fabrication, on top of the HSQ, we also deposit atomic layer deposition aluminum oxide to further seal the sample. And so in this way, any harsh deposition on top will be directly bombard aluminum oxide instead of bombard the two-dimensional material to generate defects. So with this method, at the very beginning, we see really nice dispersion, and then show the Rabi splitting as large as 40 MeV, and then the line width is as small as 8 to 9, milli-electron volts. And this is under the white light reflectivity. This is the photoluminescence. And at that time, almost 80 years ago, this sample looks really promising at the first glance. However, we try to tune the temperature. The exciton do show, tuning with the temperature, while the photon cavity line maintain constant, and we can achieve different hybridizing ratio in the lower polariton, so that they have, certain portion of the exciton, certain portion of the photon component, we can tune them at will. However, we never see a Bose-Einstein condensate with such a system, even though we make a sample as much as 600, and then we can have the Q factor as high as 1,500, but unfortunately we never see a Bose-Einstein condensate due to the intrinsic low quantum yield nature about this WS2 material, constant disulfide material, because the quantum yield in this material typically is 10 to minus 4, so essentially means you shine in laser with 10,000 photon, and then you only get one photoluminescence photon emit out. So we are struggling as a postdoc. So particularly me, I just entering the field, and then we start to look at some material like 2D material, which community people hold a lot of promise, and hoping that's go into a condensation at a really, really high temperature, because the binding energy is 300 or 400 milli-electron volts, 10 times, almost 10 times as a room temperature thermal fluctuation, but it never worked out. So I was struggling, and then it's UC Berkeley, so we have a lot of the time at that time at the chemistry department, people working in halide perovskite. I by chance know a friend, and then who introduced me to this halide perovskite material. So after reading, I quickly realized, there's a little bit of history behind it. So essentially, in the 1990s, David Meese at IBM made the first thin film with organic, inorganic hybridized material, and Professor Sotoma Miyazaki made the first solar cell based on the dye-sensitized structure with this organic, inorganic hybridized perovskite with efficiency about 3.5. And then back into the 2012, real hero Henry Snaith make it the first hybridized solar cell with efficiency all the way up to 10%. And then the material shows a great defect tolerance. And so it effectively means that if you spin coat the material without bothering the MBE or solution grow it, the material, because the nature of the material, they automatically push all the defect states outside the band gap. So it's almost no defect states in the mid gap. So which means the material has really high quantum yield. It's a good solar cell material. It's a good LED material. Many of the chemists become very excited about it. So because at that time I was struggling with excitonic, polariton, and so the quick question I asked is whether the material shows, a sizable exciton against the thermal fluctuation. The answer is yes, they do show, exciton. Plus, it's not a Franco exciton, although it's spin coated material. It's a winding mode exciton. So essentially, the exciton exists in the alkahedral of this is the ABX3 halide perovskite structure. The inorganic part is typically in the alkahedral structure, and then this exciton is mainly reside in the alkahedral structure in the perovskite. And because the material is really highly tolerant to the defect, for example, take the inorganic cesium lead chloride, bromide, iodide group for as a halide perovskite, you shine UV light on them, and then with nanoparticle synthesis in the beaker, you can really see the photoluminescence with bare eye. And such a property and combined with the sizable exciton binding energy make me really exciting about it. Plus, the photoluminescence is really tunable. The quantum yield is really high. Some of the materials, even solution process as high as 50-60%, almost comparable with the best gallium arsenide you grow over the MBE chamber. So some people also criticize, this is contains certain lead. I want to say that physicists also work with arsenide, and then for drinking water, lead and arsenide is the same level of toxic. So once we only focus on the physics experiments, we only need to use a tiny amount of lead, and which is not a big impact for the environmental concerns. So again, a stable exciton, there's stable exciton even in the room temperature in the cesium-based halide perovskite material. For cesium bromide, is the exciton binding energy is about 36 MeV. For cesium lead chloride, the exciton binding energy is about 64, 70 MeV, depends on the measurement. So essentially, if you go down to low temperature, even there are solution synthesis or CVD synthesis, you can already see the Rydberg exciton, essentially the higher principal quantum number exciton from n equal to 1, n equal to 2, and some of them, really, really great sample. You can even see something around n equal to 3. So you can start to see Rydberg series. So compare with the gallium arsenide, at the 21 Kelvin, the exciton peak is really pronounced. So this is a great material solution process without bothering any MBE growth. So the first trial in the field come from Professor Qihua Xun's group and his PhD student Rui Su. So essentially, they integrate cesium lead chloride together with hafnium oxide and silicon dioxide, DBR cavity, and then at room temperature, they already can see polariton condensation. This is back to 2017. And in one of the follow-up work we did with Rydberg exciton-polariton, we also see that they can strong coupling and using a CVD, even using a CVD sample. So however, those sample Qihua and I work is typically happen with mica substrate, and then you CVD grow this material on top. Those are typically generate a very small sample on the order of 20 micron. Although they are single crystal, you can use the Nobel Prize method like a Scotch tape, eventually transfer them into the DBR at will. But the sample size is really small, and then you can basically afford only a point-like measurement. So essentially use laser, pump it in the center, and then essentially collect the photoluminescence and see the system run into condensate. But other than that, you cannot do much beyond it. So back into 2019, I started to work as an independent group. So I took my first faculty job at the University of Nebraska-Lincoln. So it's as you all know, so Nebraska is on one hand you see this is a state in the center part of the United States, but we are largely an agriculture state. So we see a lot of cow and flatland. So indeed, Nebraska in the Indian language means flat water. And then one of the interesting thing is I asked my department chair, Jerry Harton at that time, where I can go, for some of these entertainment, things. And Jerry recommended me to visit Warren Buffett's house and see how one of the richest people, how he live in Nebraska. So. So this this agricultural land on one hand is boring. On the other hand, gave me some opportunity to think what I really want in advancing this BEC field. So back to the 2019, I spent a lot of time thinking about what is really the motivation of the field. We already know we can demonstrate the Bose-Einstein condensate at the cold atom. We already know we can study beautiful polariton physics with the condensation at the liquid helium temperature about 10 Kelvin. And as I said, there's a condensation at room temperature, but no system has really good growth or fabrication, and with the same time with the linear mode, exciton exist. And the gallium nitride, zinc oxide, organic 2D, all this past effort at room temperature seems to generate really poor result compared with gallium arsenide or cathode-telluride. So we really need to have a system that study a lot more interesting physics. For example, the quantum fluidity experiment back into the science paper, and then the XY spin Hamiltonian, the simulation of this analog things, and then we also want to study the topological physics. Emulated a lot of the things, and so those are interesting. Physics problem require we have really a homogeneous landscape. We emulate a cold atom BEC, but our solid system has to be everywhere the same atom like. We cannot like here a cesium atom, the other one is a different totally atom for this uncontrollable. So I got a lot of the wisdom from close friends of mine, that is Stephen Cohen, back to his work in reading his work in the physical review letters back to the 2008, where they show by chip bonding, a gold and gold pre-patterned DBr mirror together and fusing organic into those channels. They can form single crystal regions in the channels, and compare with without this gold bonding, where you will feel a lot of this organic become like really inhomogeneous material in this DBr cavity. The single crystal one shows quite a bit of homogeneous behavior, although the polariton mode variation at that time is 50 MeV. So I, in one of the Material Research Society meeting, I run into with Stephen Cohen. I read his paper. I think this is something, I should continue work on along the line. So I invited Stephen Cohen for a lunch together. And, at Nebraska at that time, we all know there's a Buffett lunch. So essentially you spend a lot of dollar to host a lunch with Buffett, and then you guys eat some fast food, and then but discuss a lot of the great perspective about economics and how to, how to make the right choice. But luckily, Stephen never charged me that amount of dollar. He even paid his, lunch by himself through his own funding. I think that's a really productive discussion. So I got a lot of the inspiration from the discussion, and I also think the polariton mode variation of 50 MeV is coming from the relatively not so well-designed process in bonding the two DBr chip together. The problem is coming from the DBr fabrication and how you bond them together. So I went back to Nebraska and redesigned the experiment. So instead of using a small chip, we use a big wafer. So we come into a really big 6-inch wafer and deposit DBr really careful. So the way we deposit them is by ion beam sputtering. It's people who use measure the gravity wave. They do a really sizable big mirror, and then they can make the big mirror as flat as a silicon wafer, super polished. So we do the same method, and then afterwards we pattern them with gold pillar with shadow mask. And then the evaporation is done in the wafer scale, and then all the wafer has a variation about 1 to 2% in the gold thickness. But if you, after the wafer bonding and cut into the small die, each die, they are only occupy a small area in the wafer. So the sample variation in the thickness in there is much less. So we quantify it about 0.5%. And then afterwards, we apply solution of the perovskite and run into the crystal growth into a really long time. In our case, it's 2 day to 3 day. Let the material gradually grow in the cavity, and we can see that we can grow cesium lead bromide and the layered perovskite, PI or PEA-PI, depending on how you name them, and MA lead chloride sample with a sample size or sub-millimeter size. We can further grow them, but sub-millimeter size already really big for polariton physics study. And these are the sample we make. You can see the cavity is really homogeneous, and then this is without the DBR to just see the gold pad bonding together. And then this is my students holding a tweezer. This is 1 millimeter size. We apply a perovskite solution there, let it run into these nano cavities. So a little bit of growth mechanism on this. So essentially, if we have unconfined structure, we are going to have a lot of the nucleation happen in the bulk solution. So once you have a lot of nucleation sample, you tend to grow a lot of small crystal. But if you confine this into a really small nano cavity, and then the inside the solution, you have limited side of the nucleation side, and then you have limited nucleation side, they never run into each other. They tend to grow bigger crystal, and then plus the template we have. So in this way, all the grow single crystal fill in all the nano cavity everywhere, and then we have the crystal. We have the sample also controlled by the nano cavity, not by the growth dynamic. So those materials really generate a really homogeneous excitonic emission, as demonstrated by our Nature Material paper. Here is the cesium lead bromide. Here is the cesium lead chloride. You can see them really uniform homogeneous photoluminescence. If you further quantify that by opening up the cavity and measure atomic force microscope on top, you will see the surface is really sublattice level of flatness. No rough and no roughness, and then they are really flat. And then if you close without open the cavity, just measure the lower polariton mode, you will see the polariton mode has a peak to peak variation 3 and plus and minus 3 MeV. So if you convert it into RMS variation, that means you have 1 milli-electron volts. So compared with the room temperature thermal fluctuation, RMS value is 26 MeV. So our sample only has RMS roughness about 1 MeV, milli-electron volts. So that means compared with the thermal fluctuation, our sample is really flat. You don't see any variation locally. So this also can introduce additional tunability on an exciton. So if you really make the sample of the nano cavity really small, you can even see the blue shift of it. Once we try to, in one of the draws, make it really as small as 4 nanometer of the gap, we can see this blue shift. Also shift the cesium lead bromide sample into a quantum well like 400 nanometer wavelengths. Those are really interesting experiments. With this sample, we can see really nice polariton condensation. As you can see there, we have a little bit optical bifringes due to the orthorhombic phase from the cesium lead bromide. So essentially, in plane, you have 2 index. Those are bifringes crystal, but they can do condensate at the lower polariton level, and then you see nicely G1 coherency. So essentially, you took the condensate imaging, and you took another condensate imaging, you flip them and do the interference. The left side and the right side, they show coherency build up across the whole condensate. I think after our work, I think Barbara also later on, candidly show it's not only work, this method, you can also extend it from just a hard fabricated nano-fabrication structure to PDMS template. So with the PDMS template, you can also grow, various structure with a spatial confinement. Those are really, great structure and interesting thing, to study. More detail, I think you can study Barbara's 2024 Nature paper. And then I think the PDMS mask has more defect tolerance. And then this is also another big advance in the field.
Okay, so Wei, we have one question from the audience. Can you please clarify what do you mean by quantum yield of a material?
Quantum yield of the material. So essentially, if you shine a laser to excite photoluminescence, and so the photon you pump the system has a number, and then the photoluminescence photon you collect from this semiconductor, you have another number. So you use the photoluminescence photon number divided by the pump photon number, you will get the quantum yield. So for 2D material, it's typically 10 to minus 4, 10 to minus 3. So essentially, every 1,000 photon you pump the system, or every 10,000 photon you pump the system, you typically only get one photoluminescence photon emit from the same semiconductor material.
Okay, thank you very much. I can see no further questions for now. I think everyone understood everything in the beginning, and that's probably why. So
Yeah.
we'll see more questions probably towards the end. So I'm giving the spotlight back to you.
Yeah, thanks, Miha. So I think the second part of the thing we will do a little bit faster, but run into the physics. I think we'll probably have more more questions arise from the audience. So I think, yeah, so one of the interesting thing we want to study with this grid sample is the interesting physics of superfluidity. So essentially, once the system run into superfluidity, because they run into the BEC states, what will happen is that you have many of the particles just behave like one particle. So in order to create some other excitation, you need to have the superfluidity material run into an object with the speed of velocity, with the velocity of the superfluidity larger than the critical density in order to create other excitation. For example, if you try to create an excitation with the BEC weakly interacting in the region of here, because you are running into a speed that is lower, so what's going on is there's no state you can excite. So you don't see any dissipation start to generate something like scattering, backscattering. So the liquid just is fluid dissipation less. So essentially frictionlessly flow across the object just like one particle. But if you have the excitation larger than speed, so you start to see other state, you can excite the friction and the backscattering. So those are the interesting things. See? Okay. So indeed, the lower temperature polariton system already studied this. So you have gallium arsenide sample, you burn a defect, and then you run into this polariton liquid against this defect with a flow speed downwards. So what's going on is before the polariton condensation, you will see this backscattering rings start to be formed. Then this is the K-space. You start to see the backscattering. This is the backscattering fringes. And then after you run into condensate, you start to see a superfluidity behavior, and then you don't see any backscattering ring. And if you continue increase the flow speed across the transition, where you run into classical system, you start to see linear wavefront, and then the linear wavefront open up. That essentially you always see backscattering happening in the K-space. So those are the interesting, experiments. So I want to emphasize in this experiment, the interaction is the key for the quantum fluid. If you only have a photon part without the exciton part, without interaction, you run a simulation, you quickly realize, for a laser run against the defect, you always see the scattering without, without any of the superfluidity phenomenon can happen. So in the cold atom, the superfluidity run against the defect is a relatively hard experiment because it's harder to trap an object within the evaporative cooling sample and then shake this condensate towards it. Relatively speaking, it's hard. So a lot of experiments, they are torque this superfluidity liquid in the BEC condensate and to start to show this vertex array in the cold atom experiments. So with the sample we have, we start to do the experiment by changing resonantly excite the polariton liquid. So essentially, we can use a laser to selectively pump along the polariton dispersion. And then in this way, we can control the in-plane momentum of the polariton liquid flow against the defect that one use laser to burn. Again, this is the transmission imaging of our two-dimensional sample. You can see this is almost no defect. You can selectively choose a point to burn a defect, and then the sample is very homogeneous. So the experiment runs almost identical as the gallium arsenide, but at room temperature now. You can see this, we burn a defect once before the BEC transition, the particle density is very low, and we see the backscattering. After the transition, we see the backscattering almost disappearing. Here is the simulation. Here I want to say there's a little bit winkling you see in the imaging. That's because in the superfluid physics, it's about healing length. Again, in the K-space, before transition, you see the scattering rain. After transition, you only see the resonance injection of the polariton liquid, no backscattering rain appear. Once you increase the in-plane velocity by tilting the laser angle at the higher angle, you will see, interestingly, the polariton start to open up the linearly wavefront as predicted by theory and also in good agreement with gallium arsenide experiments. And then you see the scattering rain and also other scattering features around the injection start to happen. So I want to emphasize this linearly open up the wavefront is a classical phenomenon. If you have a flat jet and then you let this go across the speed of sound to run into supersonic regime, you start to see the linear wavefront. And then this is essentially the same phenomenon. By measuring the linear open up of the wavefront, we can extract the epsilon interaction constant that is about 4 micro EV per micrometer square, a similar order as the gallium arsenide or 2D material, but 100 times larger than the organic. So in comparison with some recent work with organic in the superfluidity in the Nature Physics paper done by my colleague Stephen Cohen, Dario, and Danili, you can see in their work in the somehow in the supersonic regime, because the limit of the organic material, they don't show as nice linear wavefront opening as our perovskite case. So that indeed shows an encouraging result. Like a perovskite in this superfluidity case shows better result compared with organic and room temperature, almost comparable with the gallium arsenide. So I think the next exciting thing we try to explore with our sample to see this limit in the homogeneity and the capability is to run a classical XY Hamiltonian polariton graph simulator. Previously has been demonstrated with gallium arsenide. So essentially they optically imprint a bunch of condensate, BEC condensate, and to observe this interference, they can map the system back into XY spin Hamiltonian and by just reading this. And then the system automatically optimize the configuration and run into the minimum loss condition. So essentially you can use this as a graph simulator. I want to emphasize in the cold atom BEC community, such an XY spin Hamiltonian has been also studied. So essentially, you have a laser interference pattern, and inside the laser interference pattern, you have trapped a lot of the BEC atom cloud, and you can shape this lattice. Once you shake this lattice, the motion of degree of freedom between the lattice can emulate a magnetic system. But because the tiny motion of this atom, you can only see this in the K-space and compare with the theory. So, and this has been done in the science paper back to 2011. So essentially, the direct observation of this, Hamiltonian in the real space is relatively hard. You have to do this in the momentum space and to compare theory and experiment to see the configuration of the motion in this atom in different pockets. So it's relatively complicated experiments. So in comparison with halide perovskite, we can room temperaturely, without bothering the cryostat, optically imprint the two BEC condensate. And by observing the center part, one can see the two condensate. These are out of phase, or these are in phase, and these again out of phase, and these are in phase. So optically, one can control the pumping condition to directly tune the interaction between the two condensate. And the polariton system automatically minimize loss. So each spot density follow a relationship like that. So essentially one can map the system into spin Hamiltonian the same way as the gallium arsenide system. So we can nicely directly optically read the spin configuration in two condensate case. And interestingly, see, we want to also compare the simulation in the large XY spin Hamiltonian. Here we optically imprint 4x4 lattices. And if you compare with the gallium arsenide in the real space, we can see this almost a comparable result. But the MBE-grown gallium arsenide require liquid helium temperature, and you have MBE expensive machine. But here we can do this relatively, nicely without bothering those. And I want to emphasize both experiments, there's no feedback control to control the spin magnitude and same size to be the same. So from precisely physics, you need to have spin with the same amplitude. So you need to have the condensate at the same to have the same intensity. So this experiment has recently been done with the gallium arsenide, but just to show you the sample quality, we decided not to do any feedback to compare with the original result with the MBE-grown gallium arsenide to show the superior of our room temperature sample. Just the solution process, you can get the almost identical sample, identical physics result without bothering MBE. So there's another branch of analog emulation with a polariton lattice besides just construct a spin lattice by selectively pumping. You can construct a polariton lattice by designing the photonic potential across a 2D landscape. For example, our colleague Amo and Professor Jacqueline Block also did this nicely physical review letters paper by this polariton graphene. Essentially see the Dirac cone being formed in this C6 symmetry, polariton crystal. Those are really impressive results. But I want to emphasize this, etching such a deep DBR structure across with high aspect ratio is non-trivial, totally non-trivial. So only a couple group can master this technique, and the size of the pillar is really limited because during the etching, you are going to generate a size defect. Those are detrimental for this quantum well structure. So recent year, there's also a burst of topological insulator. We have, the quantum Hall effect. We have the spin quantum Hall effect. There's anomalous, quantum Hall effect. There has been widely proposed, and as we all know, that there's an analogy between Maxwell equation and the Schrodinger equation. So a lot of this, condensed matter, topological physics can be naturally emulated in a Maxwell equation system. For example, there's another closely related field called the topological polariton in the weakly coupling regime. So indeed, this photonic topological insulator, try to emulate a lot of the physics. For example, we have this Nature paper back to 2009 with a strong magnetic field applied. One can demonstrate a quantum Hall effect, and then we can demonstrate quantum spin Hall effect, and also a quantum anomalous Hall effect, all in the weak coupling regime. So in comparison, there's also a cold atom community trying to demonstrate a topological Hall effect with Bose-Einstein condensate on the atom with the atom platform. But I want to say that similarly as the cold atom XY spin Hamiltonian, to directly imaging the motion of the topological edge is relatively hard in the cold atom community. There's always some indirect measurement and try to back tracing from compare series with the experiment to see they have some topological quantum Hall or some other effect. So there are series with polariton community back to 2015 proposing using polariton system for quantum Hall emulation. The reasoning behind it is you have the system that is interactive. You have the photon that is stressed by the exciton. The particle has a little bit interaction, so this will enable some more interesting physics to be studied in the system. So the initial proposal in demonstrate this is by using a quantum well structure pattern or etched and apply a magnetic field and see the topological edge state propagating against the defect without the backscattering and many other interesting things. So although the first series demonstrated in the two-dimensional case that the first experimental topological laser or topological polariton laser is demonstrated by a more simple model called SSH model. So essentially, if you have a lattice side and the hopping between the lattice side are different, you will have a configuration with a trivial case where you don't have any topological band, or you have a non-trivial case where you have a localized topological edge state. The work has been demonstrated by Professor Jacqueline Block And you can see this, they etch this very hard to etch, quantum well pillar, and with 3-4 micron, with 3 micron size. And one can demonstrate this localized topological etch. As you can see here, this is the topological mode, and then this is a topological edge state they show in the paper. Once you have this topological mode start to be excited. However, one-dimensional SSH model, although the physics is interesting and rich, but from a perspective of the end result, you fabricate a lot of pillar, but you end up only localized with one pillar. And it's almost identical result as you only fabricate one pillar and start to pump. So ideally, you would rather to have two-dimensional system to start to show the propagating mode around the edge state, along all the defects. That is appear to be more interesting. So I want to say that before people run into the two-dimensional case at room temperature, there is also room temperature perovskite endeavor using the orthorhombic phase, the bifringes of the cesium lead bromide. One can automatically make the hopping in between the two different. This is done by Professor Qihua, Xiong's group, and Rui Su, and then where they can demonstrate this localized topological mode with the inside the bandgap. So there's also a lot of the effort along to demonstrate the 2D polaritonic topological insulator, done by my colleague Sven Hofflin and Sebastian Clem. So essentially, they have the quantum Hall insulator etching the gallium arsenide pillar and with certain dopants in this. But because in order to have a Z-man effect, you need to dope the crystal. So eventually, you lower the system's quality factor. And but on the other hand, in order you cannot dope it so large the magnetic atom. So that means the magnetic gap, the topological protected gap opened in the system is also a trade-off between the quality factor. So you want a large gap, you need to dope it a lot, but this sacrifices the quality factor. So it's eventually, because this trade-off, they don't open up a big band gap. They only open up a band gap about 0.1 milli-electron volt. So essentially, the system only has a band gap about 0.03 or 0.04 nanometer width. And then the polariton mode is actually condensate outside the topological gap. You have to use a filter to see this leaky process. The polariton mode observed through this leaky process, the filtering process, essentially to see the edge mode. This is not ideal. So there's no condensation of topological pure, edge states. And on the other hand, there's a quantum spin Hall insulator demonstration done by my colleague Angela Ratish at UPenn and University of Pennsylvania. So they essentially use a two-dimensional material done into a photonic crystal. And the two-dimensional material has a valley selection, so they can chirally pump the material and eventually couple with the polaritonic mode. Where the photonic crystal can open a topological bandgap large 30 MeV. And there's no magnetic field because they use a quantum spin Hall effect and in the photonic design. However, there's also no condensation or lasing about the topological edge state, simply because the poor optical performance about the 2D material, they tend to have really low quantum yield and not so reproducible, even with the one that report the polariton condensate. Those samples are typically very hard to make. So facing those challenges, we got a lot of inspiration from the topological Valley Hall designs. So essentially, the topological Valley Hall design we got directly inspiration from the 2D community. So in the 2D community, once you break the symmetry of the graphene, so essentially you make a graphene has two different atom size. You start to make the Dirac cones 6 valley become also symmetry breaking. So you have a K and a K prime valley because you have a different atom size. And with that, you can create in the science paper, once you selectively pump different values, because they have different value, they will have a Valley Hall effect because you're pumping and then the value are different. So optically, such a system can naturally extend into photonic topological valley Hall effect. Has been done by, in theory, by my colleague Gennady Sharvals, Professor Gennady Sharvals, back to his UT Austin time before he relocated to Cornell. Some similar result can also be found in the Nature material done by my postdoc advisor, Professor Xiang Zhang. And so essentially the valley Hall design is you have a photonic graphene. So essentially you have C6 symmetry. You have a hole etched in the lattice. And then what happens is you start with a photonic graphene. And then you break the symmetry and then make one atom become larger than the other atom, photonic atom. So now you have MOS2 crystal. So one atom is bigger, the other atom is smaller. So now you have the photonic valley. And then this will sensitive to the right-hand circular polarized light, left-hand circular polarized light, and those are the simulations. And if you bring the two small atoms together, photonic atom together, you will have a type A topological edge state. So essentially, the type A topological edge state is you have the solid curve. These are the two values. So if you have the two big atoms, arrange them next to each other, you will have the type B, this topological edge states along this the dashed line. So the good thing is the type B has a slightly tighter confinement on the edge, while the type A is more a little bit more dispersed out, spread out across the edge. So if you run the chain number calculation, you realize this is due to along the valley, you will have a different flip side chain number. So such a topological valley Hall design, I want to emphasize, is not perturbative. It's not robust against all kinds of perturbative. It's only robust against the C3 symmetry that a perturbation preserve the C3 symmetry. So those has a certain, so compared with the quantum Hall design, which are passive, all kinds of perturbation, this has certain limitation. But the good thing about the valley Hall design is you have a much nicer band gap to be opened up. You can have a larger band gap to be opened up, and the fabrication is relatively straightforward as well. So inspired by this, we want to first step demonstrate a pure topological edge state. So essentially here we design our polariton mode, polariton cavity. So essentially we have the DBR, and then we choose the cesium lead chloride, which is the first material that demonstrates the room temperature polariton condensation in the halide perovskite community. And we optimize the growth method and then try to make the sample really large in the solution and the CVD sample. And then we also break the C6 symmetry from a graphene-like photonic lattice into a MOS2, like we have a big atom, small atom. And at the same time, we use the type B, B type, we use the big atom adjacent to each other. So this has a tighter confinement on the edge state. And then this is a type B topological edge start to form up. And then this is the simulation one can see. And from unpatterned sample, we can see even though the upper polariton is unseen because the larger polariton Rabi splitting, we can see the flattening of this polariton mode once it's really close to the exciton line, and then one can also extract the Hopfield coefficient of this polariton mode. Yeah, by the way, Professor Hopfield recently got the Nobel Prize on artificial intelligence. So another interesting thing is we intentionally choose the cesium lead chloride is because it's compared with cesium lead bromide. Cesium lead bromide tend to be optically bifringous, but the cesium lead chloride is isotropic across the whole length field. And plus, more interestingly, compared with cesium lead bromide, which are more sensitive to the fabrication, nanofabrication, cesium lead chloride, you can optically pump this material and compare this before after photoluminescence. So you can even see this after the treatment of oxygen plasma for several minutes, and MIBK IPA development of the e-beam lithography resist. the cesium lead chloride remain unchanged in the photoluminescence quantum yield, so which is much better than the cesium lead bromide. So we optimize the sample growth. Our sample now compared with the previous one, all has a size about 100 micron. And one can directly pattern the e-beam lithography, 100 kV e-beam lithography on top. The material so robust, nothing damaged. And then the bulk simulation shows that such a crystal will have a nicely, predicted, band structure. And then the bulk experiment also matched the simulation. And then the topological interference interface experiment specifically measure the band structure in those interference in this interface. We can see this topological B-type edge start to form up in the band structure, and by selectively pumping the edge area, so one can see this nicely confined topological edge mode start to propagate against the C3 sharp turn corners without the backscattering. I want to emphasize this. If you do a AFM imaging about typical sample, you can see our sample with the pattern 70 nanometer PMMA on top. We do show a little bit variance. So the peak-to-peak variance, for example, this region is up to 10 nanometer, which is really big. But the topological, so that's make the topological edge, the topological mode a little bit, the Q factor a little bit low. On the other hand, it's because we work in the energy regime that is 400 nanometer. So that is really close to the blue light UV regimes. So that the dielectric material fabrication tend to be challenging in the DVR to have a high Q. But intrinsically, our bare cavity with PMMA, we should have a Q factor around 1,200. But after patterning, we see the drop of the Q factor about 400, 500. That is because this surface roughness of the PMMA patterning. So now we can have better method in the lab to do this. But anyway, so the Q factor is about 400, 500. But the band gap we open up here because the topological valley Hall is about 18, 14, depends sample to sample variation, milli electron volts. So we have a line width that is only a quarter to a third of this topological band edge compared with the gallium arsenide case. This is much better. And we also emphasize this, the structure we make here, the smallest feature here is about 100 nanometer. So this has never been can be possible with the gallium arsenide because gallium arsenide typically, based on my colleagues' education on me, is always a few micron, 2 or 3 micron. You cannot make the structure smaller because the etching of the DVR, the quantum well will also be damaged on the edge. Those are relatively challenging. So to show, I have a simulation. To show, here I have a simulation to show yeah, somehow this. Yeah, so yeah, I couldn't make the video running, but in our paper we also, in a supplementary video, we also show the if you run the simulation, you can see with the topological mode, you start to see the edge mode being formed here, and then they can propagate down the topological edge without backscattering. But if you pump it in the bulk region, you will see this bulk mode start to propagate out. So exactly, yeah, this bulk mode work. Yeah, you can see this pump, they smear out. So essentially that correlated to the topological edge mode, and then some of the bulk area start to show. Here you can see this. One can use a selectively filter and pump the topological edge. You can see in the bulk area they show a smear out, and in topological edge you see a little bit because the finite of our filter we have a little bit leak out. So we see a combination about some of the bulk mode, and then the the topological edge start to propagate. So that match the experimental simulation. The experiment simulation match each other. So by pumping this topological edge region into polariton condensation, you can see the condensate once with the right detuning can condensate inside the band gap of the topological gap. And then plus due to the interaction, the whole system blue shift, which indicate our photon are interactive because of polaritonic nature. And then there shows blue shift, the condensation, and then the line width narrowing. And if you do a G1 interference by making this after condensation imaging, do this left hand, take imaging and then flip it, and then to do the imaging interference, you will see this interference fringes start to show up. This is before condensation, this is after condensation, and then this is the interference you start to show up. And then for some of the nicer sample, which has less inhomogeneity, we can see this interference even build up all the way to the corner. From this sample, one can extract the G1 coherence. It's all the way up to 0.42. And then the time coherence, you can see the delay by varying the delay line, the time G1 coherence is about 2 picosecond, 1 picosecond in good correspondence to the cavities, the Q factor, and the polariton lifetime. So I want to see that the G1 coherence on the trivial bulk state is if you have just a trivial bulk state, no topological edge, you will see they only show the G1 coherence on the self interference part, and then the mode is highly localized without the propagating nature compared with the topological edge. So essentially, once it's purely run into the condensation, the whole topological edge behave like one particle and share the same coherence. So we can also enable more complicated structure. Here is a fish open mouth. Here is a fish closed mouth. And because this nice work, the editor luckily chose our work as a cover for the Nature Nano technology paper. So I want to emphasize also similar work has been done, by Professor Qihua Xiong and Rui Su's group. Great minds sometimes think alike. So they demonstrated this valley Hall edge and being formed there, but they never somehow demonstrated a circular or round triangular structure. And then they also see this chain number, differences in this K space. So beside those, we also try to use the perovskite to see whether we can see some of the electrical pump polariton laser experiment has been done by the Nature paper by Professor Sven Hoplin's group. And just give a short overview of it. So essentially, we use a silver and then the graphene, and essentially make a structure like a DBr, hexagonal boron nitride, graphene, and the cesium lead bromide, and then hexagonal graphene, hexagonal boron nitride, and the silver is the transfer process, and we use capacitance structure. So essentially, at certain time, we inject this through the graphene layer without we inject the one carrier first and inject the other carrier on the other at the other time. So this, in collaboration with my colleague, Professor Ye Yu at Peking University, we can see this nice photoluminescence, nice electroluminescence, and they overlap with each other very nicely. And so we never see the condensation with this initial trial, but the things are still working. We still try together. So in quick, I want to summarize. I hope in this short Candelas lecture, I convince you in many aspects. Cesium-based halide perovskite seems to be so far the best material for room temperature polariton physics. And many groups are working on developing methods from growth to device fabrication to advanced polaritonic in the perovskite. And our own group's collaborative work on superfluidity XY model and the topological polariton build some of the landmark for future perovskite polariton study at room temperature. With that, I want to thank my group member who make significant contribution to this work I present, especially Dr. Kai Peng, now is assistant professor at the Chinese Academy of Science, and my graduate students, Mr. Wei Li, and my collaborator, Stefan Kanakohan, Xiang Zhang, Yuye, Xiaozhe, Li Ge, and Natalie Berloff, and Graham Fleming, Allen, and Sebastian Clem, the founding agency of ONR and NSF. And this is Kai. This is my student's Wei. And with that, I want to thanks for your attention and happy to answer any questions. Thanks.
Thank you, Wei, for a fantastic, beautifully prepared lecture. And so now it's time to start the Q&A session. So far we have 2 questions from our audience, and we encourage everyone to still submit their questions while we still have Wei here available to us. Okay, so the first question is the following. Can you please explain your setup for the reflectivity and transmission measurements? How difficult or easy is it to observe the upper polariton branch?
Oh, yeah, I think that's a good question. For the upper polariton branch, I think it's relatively hard because for perovskite material, the Rabi splitting is big. It's typically 200, 100 milli-electron volts. So it's so close to the band edge absorption. So the upper polariton, once it's formed, push into the band edge absorption. So they become smear out by the band edge. So that is relatively hard. But you can see the band flattening, as our Nature Nano paper show. Regarding the setup is relatively easy. For example, a confocal microscopy. Originally, I think people somehow during the birth of the polariton, they use angle resolved photoluminescence, which is relatively complicated setup. But later on, once you have the 2-dimensional spectrometer, you just I think one can. I think in my previous slide, I do have one of this. You can just do the backfocal imaging. And for the transmission measurement, you just guide the laser through the sample from the back of it. Let me see. Yeah, you just shine laser through the back of the sample and use the same setup in the collection pass. So it's nothing complicated, I think. I think it's compared with our colleague in the cold atom BEC, this is really a poor man's experiment. Even I was at Nebraska, I can conduct experiments without bothering millions of dollars setup, right?
Yeah, that's much easier than the cold atom, that's for sure. Okay, second question. Great talk, thank you. I'm curious if you could share how large do you need to make the SSH system experimentally to see the distinct edge states like in the plots you presented and avoid the edge states hybridization that stems from the finite size effects?
Yeah. Yeah, you can see for Professor Jacqueline Block's experiments. Yeah, so they really, this is the whole pillar they make. So you can count 1, 2, 3, 4, 5, 6, 7. You only need 7 pillar along one line and then the other 7 pillar on the other line. So that's all their samples. And each of the pillar is about 3 micron size. So you don't need a large sample. But to etching this deep is challenging. For the perovskite sample, this is my colleague Qihua's one with Rui Su. You can see this 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's really limited number. You already can see this. You don't need a large number. Of course, if you have large number, the system become more dramatically observe the localization effect.
Okay, thank you. Next question. Do you see any changes in beam's shape during edge propagation? If yes, what is the longest distance with undisturbed beam propagation?
Yeah, for our case, I think the propagation length you can extract from here. The main reason is not of the perturbation that make the propagation length become limited. It's because now we have a gain and a loss system. In the polariton, its nature is a gain and a loss. So if you don't pump it to become gain, at the region, the polariton mode start to propagate, it will become loss. So you will suffer the loss of it. So it's not a scattering, but a loss. So with the polariton, we only pump in the right circle region, and then they start to propagate out. So they roughly propagate out a few micron. If you consider this natural E, like 30% or 20% of the original intensity. So a couple micron. But if you see the camera can see it with a logarithms, you can see this propagation of about 10 micron you can observe with the camera, or even longer, barely by your eye. But if you start to pump it, the whole channel area or the whole bulk area, to make it condensate, and because the everywhere become gain spectrum, they essentially propagate forever without damaging. Yeah.
Okay. Okay, thanks. Another question. How stable is the perovskite sample under laser pump?
Yeah. So I think I want to say that. So for sodium lead chloride is super stable. So because think about sodium lead chloride, they work in the region about 430 nanometer. 430 nanometer, the polariton mode. And what happened is you have a DBR structure that's centered around 430 nanometer. And then that means you have a bandwidth. So that means you have to pump about 350, 360, 370 nanometer. So which already means your femtosecond laser or CW laser has to go into a UV regime. So we have PMMA on top. The typical experiment we observe is the PMMA damage first, but the process still works fine. So the experimental phenomenon is once you go to 5 times the threshold, you start to see a dark spot because the PMMA is a polymer start to be burned out by the UV laser. But the perovskite, you can transfer them and then wash away, they still work. So recently we have a method to get rid of PMMA, so I think the case become much better. So I would say as long as you use the femtosecond laser pump to minimize the heat, and the cesium lead chloride, you can do this in the air for almost 10 times, 20 times threshold without damaging. They are fairly stable. Yeah.
Okay, yeah, seems very stable to me. Okay, another question. Great lecture, thank you. How can one distinguish whether an edge state is topologically non-trivial rather than simply having a different energy due to being at the edge of the chain?
Being the edge of the chain. So the topological trivial and the non-trivial I show here. So this is the topological edge state that you see the G1 coherence start to build everywhere. And you can make you can make the sharp turn without losing the intensity C3 sharp turn. For the trivial mode, it's typically isolated. They don't propagate against this. And then for simulation, for series simulation, I think the topological trivial mode, you pump it locally, they smear out. I don't know why this one doesn't work. Yeah, so for the edge mode, they can propagate without loss. So essentially, so anything that stay in the edge, because there's a bandgap, there's no allowed bulk mode. So only the edge mode allowed there. So once you see something propagate against the sharp turn, that's the edge mode. That's smoking gun proof. Side evidence is they show G1 coherence. Yeah.
Okay, thank you. Next question. Are your perovskites synthesized in nitrogen environment?
Oh no, you can't do that. I say that. So in the cesium lead bromide case, I think it's more fragile. It's better to synthesis in global, but you still can synthesis under air environment. You have some detrimental effect, but not so easy to noticeable. But for cesium lead chloride, I would say almost identical synthesis once you're in the air or in the global. So it's way stable than you think. Think about our experiment has 100 EV, 100 keV E-beam lithography directly on top, nothing damaged. Think about we have oxygen plasma treatment before we coat the PMMA on top for 2 minutes. So I think it's really a robust material. The only thing that is a little bit annoying is you have to have a laser that excites them with 370 nanometer wavelengths. And then the growth is compared with the cesium lead bromide is a little bit non-trivial. we do spend a little bit of time to figuring out how to grow this material big, but we wrote everything in the supplementary and in the method section in the Nature Nano paper. I invite people read those sections. Those sections cost my graduate student almost 10 months to figure out. Yeah, but we try to write it as detailed as possible to let other people reproduce our result.
That's a great way to do it. Okay, another question, and I think the last one today. What will decide the condensate happen in which state, in which level, which it always condensate at edge state? Oh,
yeah,
it's hard to understand, sorry.
Yeah, so we have the continuous band of this is a good question. I think we have a continuous band of edge states, right? Eventually, we have no control. We have some control, but we have no deterministic control to let it condensate at a certain point, right? So eventually, the system chooses by the material's gain spectrum. So essentially, the photoluminescence has a quantum yield where certain area of the gain spectrum like to condensate more. So essentially, you have a gain loss system. Your gain at certain spectral region always want to condensate first. So we can making the patterning. We know that the region that's always want to condensate is in the region of 429, 428 region. So we make the topological gap center around that. So once you pump, you have a little blue shift. You still condensate in that region. So we selectively tune the samples so that the topological edge in the region that is typical unpatterned sample like to condensate, we make that is our topological gap region so that eventually they will condensate in that region. I think the same thing for the gallium arsenide, right? They have certain spectral region like to condensate, and you make the sample topological edge in there, in that region by changing the detuning of it. So essentially, the detuning is the exciton photon position, relatively position of it.